Builder here. In this episode of Zig in Depth, we're going to be talking about formatted output in Zig. And let's start out with, basically, we have here much of this file that we have here, this main.zig, is the default main.zig that is produced when you do zig init exe. I left in a lot of that content because it is relevant to the topic of formatted printing. First of all, we are going to have a demonstration of how to use debug print. And if you've been watching the previous videos in this series, you're going to be already familiar with this. Debug print is a quick and easy way to print, but you have to be aware debug print is not meant to be the primary output mechanism of your program, because it doesn't print to standard output, it prints to standard error. It's easy to use debug print because it doesn't produce any errors. It can't fail the way it's been implemented. So you don't have to use try, and you don't have to use it in a context where you handle errors. So that makes it a quick and easy tool for debugging. But you have to remember, it can't be your primary means of producing output. If you do need to produce output for standard error in your application, then you can use debug print, or you could use directly the standard error output stream that you can also get a handle to via the standard library. But here we'll be demonstrating debug print. And as you may have noticed, there's always the first argument we're passing is a format string. This format string has to be comp time known, okay? You can't pick up this string, for example, from a command line argument or read it from a file or things like that. It has to be directly in your source code, because Zig processes this format string at compile time, okay? So if you have errors in your format string, they will be reported as compile errors before the program executes. That's a really big advantage, and also a testament to the power of comp time in Zig. The fact that these formatting functions are all implemented at compile time and using the language itself without any special compiler tricks or magic. The implementations are right there in the standard library, okay? So we have the format string, and then here usually you're going to see that we have what we've come to know as the tuple literal syntax with the dot and the curly braces, which allows you to provide a list of arguments, okay? And these arguments have to match up with the placeholders that you have in your format string, okay? Here, the placeholder is curly brace S, okay? Which is what's known as a format specifier for anything that's a slice. We're going to see that in a while, okay? So here we're basically printing out just one argument, which is a string literal that we have right here. And that's basically it for debug print. Now, when you actually want to print output to the standard out, and remember that standard out is not necessarily a terminal screen. If you are working in an environment where your program is like a filter, and much like the context of Unix pipes, where the output of one program is the input of another, then your standard out could be the actual data that your program is producing. Here we have an example. They mentioned that, for example, if you're implementing a tool like gzip, that kind of tool that takes in some data, compresses it, and produces the compressed bytes. Its standard output isn't meant to be displayed on a terminal screen. It's meant to be either passed on to another program or written to a file, okay? So you have to think about the standard output stream in a wider context like that. And here we have a demonstration of how to get a handle to the standard out. We use here the stud IO get stud out function, and that produces the handle to the standard out, but we actually need the writer, okay? And in the standard library, we're going to see this type of convention commonly used when we want to do any kind of writing of data. We call a writer method to obtain the actual writer that we can use to write to. It's basically the writer interface in the standard library from stud.io. And once we have that, we are going to create a buffered writer, which will provide buffering for our writes, okay? And this is a really important detail to have in mind, because when you are writing, for example, directly to a file or to a network or to just the normal standard out, that requires performing system calls, which are costly. They have an overhead cost. And if you can buffer those writes, and buffering in that sense is just holding a location in memory where you can write to that location in memory, which is much faster than performing the syscalls, and then only perform a few syscalls when you want to actually do the writing to wherever you're going to write. So this provides a huge performance boost when you are performing this type of I/O. So this follows the methodology of wrapping a writer around another writer. So we're wrapping here a buffered writer around our stud out instance of a writer. And finally, from that buffered writer, we call the writer method to obtain the actual writer that we're going to be using, and that we assign to this constant stud out, okay? And then with that, we can print, okay? And this print method is going to be basically just like the print method on debug, okay? It takes the same parameters, the format string and the arguments, but you will notice that here we are using try, okay? Because now we are actually writing to the standard out, and in this case, we have to be able to handle the error condition if any error happens when we try to write, okay? Which could happen. Now we're going to see some examples of using different types of formatting for different types of values, and I copied this line here from the standard library documentation, and it demonstrates the expanded complete syntax for a format specifier, which would be one of these placeholders that you have between the curly braces. As you can see here, we have the opening curly brace and the closing curly brace here, and you can have all of this in between, and they are mostly optional parts. And we start out here, this one that says argument is, you can specify the index of the argument that you are trying to format. Usually you don't see this index being used. For example, here we have just the empty curly braces, and this will then work in a positional form. So since this is the first placeholder we have in our format string, it'll match up with the first argument that we have over here in our arguments. But as you can see, we only have here one argument, and we have a whole bunch of format specifiers. So that's where the index here, the argument, comes into play, because here the second one, we have a 0 as the index. So it's saying that this format specifier also applies to the first argument, which is here float, and this one too, and this one too, okay? So you can have many format specifiers applying to a single argument using that argument option. Okay. Now next, after the argument, you can provide the actual specifier, the actual format specifier itself. And the format specifier is what dictates how that value is going to be formatted. Here we don't specify any format specifier, so it'll default to the default format for the type that you're working with. In this case, a float. Okay. Here we're specifying the letter D, so it'll format that number as a decimal number. And here we have the letter D with some additional formatting options after the colon. Okay, we're going to see this in a while. So as you can see, after the argument, if there is an argument, we would have the actual format specifier. Then, separated with a colon, we would have, if we're going to be using a fill or padding, in the case where we specify a width that's larger than the actual value, we can specify a fill or a padding value, and that extra space is going to be filled with this value that you specify here. It's a single character. It can only be a single character, and it'll be used to fill that space. We are making use of that here. The 0 would be that padding in this case, in this example. Okay. Next up, we have the alignment, and the alignment can be any one of 3 characters, either the less than here, which is left align, so it points to the left, the caret here, which points up, which basically center align, and the greater than sign, which points to the right, which is right align. Okay, so if the width is greater than the width of the value will be aligned according to those 3 characters. And then we have the actual width. You can specify the width. Here, for example, we're specifying a width of 10. And if you're dealing with a number, you can specify a precision after a dot. Okay, and that would be the number of decimal places after the decimal point. Okay, so here we're specifying 2. Okay. So what we're doing is precisely we're defining here a float, an F64, and we're using these different format specifiers to format that same float variable. Okay, so let's go to the other terminal, take a look at that output, and that would be let's scroll here. Here we have the initial output lines from the test of debug print and the standard out print. And here is where we have our line that formats the float. Okay. First, we have the default formatting when we don't specify any formatting for the value. It uses the scientific notation with the exponent. Here we have the version where we use the D format specifier, which formats it as a decimal number. Here we have formatting as a decimal number with a width of 10, and we are left aligning our value. Here we are center aligning, and here we are right aligning the value. Okay, and in each of these we only specified 2 decimal places after the decimal point. Okay, so let's keep on going here to the next value type, which would be an integer. And as you can see, we can format integers as decimal, as binary, octal, hexadecimal, as an ASCII character, and this will only work if that value is in the range of an 8-bit number, so from 0 to 255, and as a Unicode character, which would only work if it's in the range of a 21-bit character, okay, which is basically the range of all of the Unicode code points. Okay, So if we go back here to the output, here we have the decimal form, 42, the binary, an octal, hexadecimal. We have as 42 as an ASCII character is the asterisk, and in Unicode it's the same because Unicode, in this case UTF-8, is a superset of ASCII. So those first 8-bit range code points are the same, okay, as ASCII. Now let's take a look at if we are dealing with a string or anything that can be sliced, as we saw in the video about pointers and also arrays. We have different pointers in Zig that can be used with the slice operator, and arrays and slices. We can use the S format specifier in those cases. And as you can see, we can also use the fill here. We're going to use the underscore, we're going to center align, and we give it a width of 20. So we can do some formatting of text this way. And here in the output, here we go. We have the normal formatting here, and here we have with the padding, okay? Using the underscore and center alignment. Next up, we have an optional, in this case an optional U8, and for this we can use the question mark format specifier. And aside from using the plain question mark, we can also add formatting after the question mark if we are aware of what type of data in the case that it isn't null. So here we know it's a number, so we're formatting as a decimal number with 0 as a padding, right aligned, and 10 as the width, okay? And that's what we have here. Here is normal formatting in the case where we have a value, and in the case where it's null, it'll format it as the actual text null. And here is when we have a value and we apply the other formatting options. Next up, we have an error union, and this is basically the same, but instead of the question mark, we have the exclamation point, okay? So once again, we can also specify the exclamation point and some extra formatting for the value in the case of success when there's no error. And that's what we have here. In the case of an error, we get the error spelled out as text. In the case of success, we get the actual value, and here we see that you can format the value, okay? Next up, we have here, we're creating a pointer to our float with the address of operator. And we're going to see that if we use default formatting or we use the asterisk, we're going to get the actual address, the type and the address of that pointer. And here we also have the argument of dereferencing the pointer, so we should get the actual value, okay? So let's look at that output. We have it right here, and as you can see, when it's a pointer and we don't dereference it, we get the type at and the address, okay? And when we use the asterisk, it's exactly the same. And here, when we dereference, it's the floating point value, okay? Next up, we are going to be seeing here the case where we have a struct, has a Boolean field, has a float field. We create here an instance of that struct. We don't provide anything in the initialization because both fields have default values. And here's a little gotcha that happens to many people when they are new to Zig. It happened to me. It's the fact that if you have a struct and you're going to be using it with these types of formatting functions, then you can use it directly, and you can access the fields by name by putting them in square brackets. Okay, so here we want to use the value of the A field, and here the value of the B field. Okay, and we can, just like with the other cases, we can add additional formatting here as a decimal number. 0 padded, right aligned, width 10, position 2. And we pass, instead of passing a tuple, we pass the actual struct, okay, itself. This does basically the same thing as this, which is what I was doing for a long time before I realized I could just use the struct directly. Instead of using the struct, I was using the actual tuple literal syntax as always, and then providing the different fields of the struct individually. But you can do this, but you don't have to. You can do it this way, and I think it's a little clearer because you can use the actual field names here in the format specifiers. Okay, so if we go here to the output, we have here, we have the S variable that holds an instance to that S struct. The first field is true here, and we have the second field, the floating point formatted. Okay, and here is the same output using the tuple literal form. Okay, so you should be mostly using this instead of this. Okay, now we're going to see an example of how the standard library in the FUMPT namespace provides functions. Sometimes you have to produce a formatted string, but not to print it out to an output device, but to use it further on in your program. And there are two options. If you know what the width or the size of that string is going to be, it's going to be within a certain size limit. You can use a fixed size array, like here. We're separating 256 bytes on the stack here with an array. And we can use the function buff print, which takes a slice as its first parameter. And here we're passing in the address of that buffer, which will coerce to a slice. And the next parameters are exactly the parameters that we pass to the formatting functions that we've seen, the format string and the actual arguments, in this case, the struct, once again, okay, that we'll be using. And that will return the slice of this fixed array, the slice that was actually written, okay? So when we print that out, it will print just the slice with the bytes that were written of the formatted values, okay? So we have this here. This is stir. And once again, we have the true and the two fields from the struct. But this time as a slice of an array that we created here on the stack. Or we have the situation where we don't know the size ahead of time. So we need an allocator. Here we're creating an instance of the GPA, okay? And we are using, in this case, the alloc print function from stud_fumt. And in this case, we pass in the allocator as the first parameter, and the other two parameters are just the same as we've seen before, okay? And in this case, it'll use the allocator to allocate bytes for that formatted output, which we have to remember to free. We're going to receive those bytes as a slice here in stir alloc. And we have to remember here we're going to use defer to free it at the end of this scope. And here we use then the normal start out print to print out that produce slice with the S format specifier, which is what we have here in stir alloc, okay? Same output. So you have those two options also in terms of producing strings that you can use further along in your program. Here we have a demonstration if you need a literal curly brace in your formatted output. Since the curly braces are special, they're used for the specifiers themselves. All you have to do is double them up, repeat them. So when you want a single curly brace in your output, you use two curly braces, okay? So here, instead of this being the S format specifier, it's going to be the actual literal curly brace, the S, and the literal closing curly brace, okay? And that's what we have in the output. Let's scroll down here. right here where it says curly, and there you go. You have the literal curly braces with the S. That's good when you're generating code. You're actually generating, for example, Zig code that has those format specifiers. You can do it with that. And here we have an example of when you're using a buffered writer, you have to flush at the end. This will write out any remaining bytes that could be in memory in the buffer. It's really important to remember this because if you don't, then you could get incomplete output. Okay. And here now we're going to take a look at pretty much a demonstration that all of this that we have seen for the formatting functions work for pretty much any type of instance of outputting text in Zig. It could be using the debug print, it could be using the logging facility. Here we see the different logging functions: debug, info, warn, error, okay? And also like we saw with the stud out. So basically any type of writer that has a print method or in the logging methods, okay, will work exactly the same with the format string and the arguments that you pass in, okay? So that's what we see right here, okay, with the different log levels here: debug, info, warn, and error, and the debug print, okay? And finally, we have a final format specifier is any, okay? And any basically will print anything using a default formatting provided by the language. And this is really good for debugging, okay? So for example, in the case of structs, you're going to see all the fields. That's what we're going to see here. Here we see in the case of the struct, it's telling us the type. It's a main.s. It gives us the field names and their values. Here in the case of the string, it's telling us that it's actually a sentinel terminated array with 13 elements of U8, and it gives us the address, okay, the pointer, because it's a pointer to this array, okay. And here we get the actual floating point value, okay. So with that, that's basically it for formatted printing in Zig. As you can see, there's a lot of flexibility, and the good thing is that it's a standard interface that you can use with basically any situation where you have to format a string in Zig to either output to an output device or to use further in your program, okay? So do the builder here. I'll see you in the next one.